Hi everyone, welcome to Evernote Day 16. The floor will be lava. This video I'll be going over the problem and my solution written in Python. Yeah, let's do it. So in this problem, we have inputs that look like this, where we can think of this as sort of a 2D plane, where the dots are empty space and these lines are mirrors. So we have an energy beam that's passing through this grid, and it passes through the empty space without interacting. But when it hits a mirror, um, it bounces off. So yeah, we can just go over the rules for the mirrors. The energy beam will start in this top left corner and is going to the right. When it hits a mirror that's facing like this, it gets pushed, or it gets rerouted in a 90-degree direction. So for example, one coming from left to right, hitting this mirror, would start going down. Similarly, if it was coming up, hit this mirror, it would start going left. And then from the top, it would start going right. Then from the right, it would start going up. Then we have the forward slash, which just sort of also pushes um, reflects the beams at 90-degree angles, but just in sort of the opposite direction. So this one coming from the right goes up, and so on for the other four directions. Then we have these um, flat mirrors that can either be oriented vertically or horizontally. That's like just like this pipe and the dash. So when we hit, so say we have a beam of light that's going from left to right along this third row. If we hit a mirror that's facing perpendicular to the path of the light, so for example, we're going horizontal, hitting a vertical mirror, we shoot out two new beams um, going in the 90-degree direction, so that original beam is canceled out. So here we would shoot up and down and not continue through the mirror. Similarly, for this dash, if we are coming up, we'd shoot off to the left and right and not continue up. Then if we hit one of these mirrors on like the flat, or I guess like narrow direction, however you want to call that, not the face of the mirror. So for example, we're here going up, we would pass right through and not interact with that mirror. So essentially, the beam comes in from the right, it hits this mirror, goes up and down, down hits this mirror, goes left and right, no interaction, goes up. You can see it sort of bounces around in here. But what we care about is for each one of these points in the grid, whether that's a mirror or empty space, does like the laser beam travel through there? We count up how many um, of those squares have the laser beam going through them. We call those sort of energized squares, and that's our answer. So here's just using arrows to show what this looks like in the input, in the sample input, and then these are the energized tiles. Notably, we can see that something we'll have to think about is that a beam can be traveling through the same square in multiple directions. So we could have the mirrors being arranged such that the beam is traveling this way, gets reflected around, and then is traveling like this. So we'd have at this point, the beam would be passing through it twice. We still need to only count that as like being energized once. So let's get into how we actually approach this problem. So got my code arranged, um, where part one and part two are in separate functions. You can see that in part one, I'm just counting this using this count energized utility function. What this is going to do, and just returning what it gives you. What this function does is it essentially counts the energized tiles with an input of lines. And then a start. The start is a tuple of four integers, where those are the first integer is the x position of this beam, the second is the y position, then we have, or sorry, not x and y, we're thinking about row. Here, look to the sign, row, column, d row, which is like the difference in the rows. So that's going to be 1, 0, or -1. and decall. So again, going to be 1, 0, -1. For example, if we have this beam traveling to the right, the difference each step, moving 0 rows because it's staying on the same row and increasing its column index by 1. So we'd have d row of 0 and decall of 1. It's important that we keep track of all 4 of these because the beam needs to be described as its position, which would be like the row and column, and its direction, which is the d row and decall. Then essentially what we're doing is iteratively we're keeping track of a stack of these points or like laser beam positions where the position again includes the row and column index as well as the direction. We're going to iterate over until the stack is empty, which means we've tracked the laser through till it's either escaped the input or just been reflected back into a loop. When we have like this laser beam position, we can first validate that it's still in the grid. If not, we just continue. Then we check whether it's in this scene set, where if we've seen the laser beam in this position before, we can continue. We've already processed it. And then we add it to the hash map, and then just perform a little bit of logic based on what the current tile is. You can read through this in more detail. I'm not going to go into every single one of these little cases, but essentially if, for example, we have empty space, the new position is the row plus the d row, call plus decall, and then the direction d row and decall stay the same. Then for these flat mirrors, we need to check if it's passing through or if it creates two 90-degree beams. We can see in that case, we are actually increasing the size of the stack. We're appending 2 values. Similarly, for the other mirrors, you can look into more detail on what this does. Finally, what we do is we want to return the number of energized tiles, which is the number of elements in this set that have unique row and column indices. So since we're keeping track of the direction for this scene set, but we don't care about that for the energized tiles. So here, we just create a set of those unique positions and return the length of it. Running that, we can just run it on the example actually. Get a part 1 solution of 46, which is correct. Now going on to part 2, what we're doing is instead of just shooting in the laser from the top right, we're taking every way we can like initially shoot the laser in, which means from the left position at any of these rows, so going like this, like this, like this, like this, all the way down. Similarly, from the right side, going in like this, 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 this. Then we have from the top, like this, or sorry, coming down from the top and up from the bottom. So essentially, and then for each one of those initial laser positions, we want to count the number of energized tiles and return the maximum over all of those initial positions. So since we have this handy count energized function, all that looks like is we create this list of energy totals and we're iterating over the starting positions from the left and right and the top and bottom and just returning the maximum of that list. Here for the example, we get 51. And that is correct. So yeah, that's it for day 16. Pretty straightforward, but a little bit challenging maybe to debug all of these cases for the logic of how the laser beam bounces around. That's it for this video. Thanks for watching. If you have any questions or comments, please leave them below. And yeah, I'll see you in the next one.